Hi, everyone. Considering I'm the only solar physicist in the room, as far as I'm aware, I think I should frame my research a little, maybe. So as you may or may not be aware, the solar surface is around 5,000 to 6,000 Kelvin, but actually the outer layer of the atmosphere, the corona, is around 1,000,000 Kelvin, which is a pretty odd thing considering we're moving away from a hot object and it's getting hotter. This is known as a coronal heating problem, and it's one of the biggest outstanding problems in solar physics. But I'm not really focusing on that. Rather than asking that question, I'm wondering about these structures you can see here, which are called prominences, which are actually cool structures that are forming in this super hot environment. So the question then becomes, how are these cool structures forming? Maybe why is it important that we understand this? That reason you can see here in this video, where you can see that these structures can erupt. And if any of these structures erupt aimed at Earth, we might have some very aggressive solar storms that we need to deal with. Now, the simulation I'm about to show you.
What time scale was that? How long? Is that like a day, an hour, a year? That video.
Oh, this is
a video, but
it should be like a couple of hours.
So yeah, thank you.
So to frame the simulation I'm about to show you, I have to talk about current sheets, which don't only occur in the solar atmosphere, also throughout our universe. But so the idea is very simple. We have a magnetic field that changes its orientation across some surface, and that is associated with an electric current in that surface. I should note in my simulation, it's not changing 2D, it's sort of rotating across this plane, which is important for the structure forming. But important to know about this current sheet here is that in ideal magnetohydrodynamics, which is a fluid model we're using to describe the plasma, this is a stable structure, but if we include non-ideal effects like resistivity, we get a tearing instability, which will break and reconnect our magnetic field lines when they are pushed together, as you can see in the animation on the left, creating these islands as seen on the bottom. And then the second type of instability I'm looking at is when I'm including thermal conduction, radiative cooling, and background heating, we also get a thermal instability, which will cause the plasma to condense to these cooler structures. So I was interested in seeing how these two interact. And I'll show you the animation first, maybe. So on the left, we have temperature. On the right, we have density. I indicated how the magnetic field is pointing. And this is a 3D simulation, but taking the z=0 plane. So first, we have the tearing instability creating these island structures. And only at a later point here, you can see that the thermal instability is causing the plasma to form condensations at the center of these plasmoid structures. I don't really like the picture I'm about to show you, but it will give you a good sense of what it looks like in 3D. Here the red is basically showing the hottest region at the end of the simulation. The blue is the coolest region. And then the spiraling things you see are trace magnetic field lines. So you get this like helical structure going around these condensations, which explains like the ribbon-like structure you saw in the beginning in the video. So the analysis I then performed on this was almost exclusively done with YT. So in the left panel here, the first thing I wanted to check is if I take a cut across this simulation, I should recover a profile that's very typical of the tearing instability, and that is this profile shown here on the bottom left is a very typical tearing profile. So we're very sure this is a tearing instability acting first. And then on the right here, you can see some time series analysis I did, where in the top panel, I'm showing that at a point, the temperature goes down, the density goes up. Why is that? That's because the thermal instability or the thermal runaway effect is such that when your temperature decreases, that will actually lead to an increase in density, but that increases the radiative cooling in the system. And so the temperature will decrease further and we get a runaway effect. And you can see very nicely how this density and temperature are linked here. And in the bottom, I did an analysis of the energy. Now this is for the entire simulation box. The reason I looked at this is because in these magnetic reconnection events, a lot of the magnetic energy is converted into kinetic and internal energy, mostly at the reconnection point. So in the future, I will definitely be using some of the region selection tools in YT to look at these regions in detail. But so this is for the entire simulation box. And then I used YT to also define a derived field on the left here, which is quantifying my radiative cooling term. So this is a snapshot right before the one on the right here. And you can see very nicely that radiative cooling is occurring most here in these wings of the structure. Remarkably, it's not occurring as much on axis where it is actually coolest. And then finally, I would like to end with the reason why I'm here to connect with all of you. And that is when I advertised the workshop in our research group, a lot of people said to me, we would love to use YT, but, and that is because they are working on space weather modeling, where they are running simulations where, okay, they're leaving out the sun here in the middle, but they're sort of simulating what is coming out of the sun in all three directions. So these are 3D simulations. And these simulations are run on stretched spherical grids with multiple levels of mesh refinement. So you may refine like once in the red box and then once in the orange box. But unfortunately, the YT website says that at present stretched grids are restricted to a single level of refinement. I fixed it. So we hope that, or my hope is that we can maybe work on this week or get started to work on this week, such that these other people in my research group can also start using YT breach. Thank you.